Hello, everyone. Welcome to Healthcare NLP Summit. So today I'm going to cover some benchmarks that we collected while evaluating real-world applications using medical large language models. This is Veysel Kocaman, CTO of Johnson Labs. Welcome again. So during my session, I'm going to cover certain aspects of benchmarks and then LLM real-world applications. The first one is information extraction, and then the data, and then the text and image identification, medical terminology mapping, and then clinical notes and relation with LLMs. So information extraction is the backbone of classic natural language processing, as you may know. So given a clinical text or one single sentence, we usually would like to extract a whole bunch of information that you see on my screen right now. So you may extract named entities, you can find a relationship between these entities, and then you can map these entities to certain medical terminologies. So Johnson Labs has been in this domain for the last 10 years, as you know. So we have more than 2,500 pre-trained clinical models that you can use on your own data by just getting the license of the library. So then we wanted to, but with the advent of LLM, people started to throw LLM at each problem, right? So even a simple information extraction task, they are trying to use LLM. People tend to use because it's easy to make an API call to ChatGPT, right? You can just easily make a call to Anthropic or GPT 4.5 and then get results instantly, rather than people install a bunch of other stuff or install some heavy libraries on your own infra. But the reality is that for POC, it is nice to do this. You can easily test your ideas and then build some quick POCs. But when it comes to production, because of its expensive nature of LLMs and non-deterministic nature, and then you can easily go bankrupt if you try to process 100 million clinical notes to extract 3 entities with LLM, right? So it would take days, and at the end of the day, you would pay around $1 million just to extract 3 simple entities, right? So there is a recent paper talking about this as well. They fine-tuned Llama 3.57 to be one of the most prominent and popular open source LLM out there that you can fine-tune with your own data. You can extract bunch of prompt or just use some agent frameworks to write a prompt for yourself and then extract entities. But when it comes to accuracy performance, the reality is that even with the best 8-shot performance, this is what paper says, by the way, they were able to hit 70% strict F1 score for entity extraction, which means that even if you fine-tune that, this is the even they fine-tune the prompt, improve the prompt with some examples, we call it 5-shot, right? They were still be able to they were still not able to achieve above 90% accuracy over there. So another one is like we published a few months ago as well. They compared classics like vanilla NLP approaches to LLM approaches like GPT 3.5 and 4, and then even CRF result, which is like maybe 20 years old algorithm over there, or clinical birth, which is again less than 10 years old, right? You can achieve better results than GPT-4, which was state of the art a few months ago, as you know. So this experiments tell us something, that you don't need LLM for such problems, and especially if you are trying to achieve high accuracy, like detect PHI information, sensitive information, or extract all the biomarkers, right? Maybe you are going to build some other tools or make some diagnosis based on this information that you extract. You cannot trust undeterministic models, or if you want to process millions of records with these LLMs, even if you are sure that it is doing really well, the cost and computational concerns will definitely hit you back. So that's why we wanted to evaluate our model. Since the advent of ChatGPT, there were even some commercial cloud providers that you can hit easily via endpoint and then extract entities, right? All the bunch of entities you can extract. And then You don't need to worry about the installing any other library on your prem again, so it's easy. Your data is secure over there because they have private cloud as well. But the accuracy is still a concern over there because they are still black box. You don't know what's running behind this, and then they provide you a set of entities that you see on the left-hand side of my screen, right? For example, Google Cloud. All big cloud providers have their own healthcare NLP service, let's say, that you can hit and extract entities given your text, which means that in Google Cloud, there are a bunch of entities that you can extract. In Azure, there are other type of entities, and AWS, Medical Comprehend, there are other types of as well. But as you see, there are a handful of entities over there. But at Johnson Wales right now, just for problem entities, symptom disorder entities, we have more than 20 different variation, like a granular level of entities that could be regarded as disorder entity. For tests, we have more than 10 different entities, etc., which means that when it comes to granularity and customization, you would like to have a full control over your own data and own your code and your pipeline. Especially with the help of some vibe coding, right? Some coding assistant tools, you can even build these pipelines without writing any single line of code, because this is the popular library that you can't get any other third-party code editor to or LLM to write your own pipeline to extract all these entities. And as I said before, you can extract more than 400 different entities from 130 models, because the higher the number of the entities, the less LLM will differentiate between these entities, right? Because when it comes to sign and symptom and disorder and problem, these are all similar terms that LLM might confuse easily. So that's why we usually tend to group all these entities under some major categories so that LLM's job is much easier over there. Then we compared our solution against Azure, AWS, GCP, as well as GPT 4.5, which is the latest model by OpenAI, and Anthropic Sonnet 3.7, which is again the latest best model provided by Anthropic. So we pick around nine entities to evaluate these models based on their popularity on a clinical text. We wanted to be more general terms rather than more granular terms. And then we annotated them via in-house annotators, physicians, and then wanted to test our models against these entities. And as you see, our models are usually doing 5 to 6 times less error than the other models. Like the closer competitor would be over there, like a GCP and Azure. So this also highlights the same findings, right? Like the LLM itself, 2.5, GPT 2.5, and then Anthropic Sonnet, the most capable LLMs out there, which are doing really well when it comes to general task, reasoning task, etc. But when it comes to extracting entities, small and like short, like just a few token entities, they are doing bad because they are not trained in a way to accomplish this test. And then for entity extraction, you don't need LLM anyway, because you can achieve the same goal with like 10 megabyte size of model in a much faster and more accurate way. So the next task was we wanted to test if the assertion status detection can be achieved by LLM as well, because the assertion status is more of an understanding than an entity extraction. It is like given a neighboring context, extracting is negativity scope. Like, for example, the patient gets a short of breath when he's doing something else. So this is a conditional situation. So why is this important? If your clinical mode is talking about some absent or hypothetical conditions, and then you are trying to create some subcohort based on the occurrences of all these entities. If you don't check their assertion status, you end up with the patients which have no disease or with disease belonging to patient's history or patient's family members. So that's why assertion status detection is one of the most popular application of NLP in healthcare NLP domain. So we did the same, and then we just annotated our own data, and then wanted to evaluate this model against LLMs and cloud providers as well. So in Johnson Wales, there are 5 ways of doing this when it comes to assertion status. Like, we have different techniques. We even wrote a paper about this, but we don't have time right now to go over this, but we have a paper that is just published, by the way, last week. And then with the help of all this modularity and then all this combination, we can modify these pipelines in a way that can extract the most extract the assertion in the most accurate way. right? You can just use one model, or you can use 3 model and then combine them within the same pipeline. If you don't like, let's say, the results from the possible entities or absent entities, you can go ahead and then check that or replace that stage or fine tune that stage with your own data and then build the pipeline again. So compared to GPT-4o and Azure and AWS, as you see, the models trained by Johnson Labs are doing much better compared to other commercial solutions or open source NegEx solutions, as you see. So as I said, we have a paper. You can go to this archive link and then check the paper. We explain all the stages over there in detail. And we just don't have that 6 labels, 6 assertion status. We have more than this actually, which means given each domain, we have different assertion status labels. Like when it comes to radiology, we have three labels like confirmed, negative, suspected. But when it comes to oncology, we have the popular one like present, past, possible, etc. So you can go ahead and then check these models in our model hub as well. We have more than 100 pre-trained clinical assertion models that you can test. And the next step was medical terminology mapping. You have the entities, you have the negative scope. Now you want to map this to ICD time code, Ariston or SNOMED for billing purposes, for some claim reporting, etc. Right? So Johnson Wallace already have a medical terminology mapping application, which is powered by all these NLP models that we have been working on, but you can still code this up by yourself. So we wanted to evaluate one of our models like Ariston extraction, evaluate this model against LLMs as well, and then the other cloud providers as well. As you might guess, LLMs are not designed in a way to extract ICD time codes or Ariston code, right? Because it needs to find the entities at first and then map to terminologies. But you can achieve this with some simple vector DB approach or in a way that we do, rather than LLM, because LLMs are not databases. They are not there to extract information unless it already memorized. Of course, it will return something. As you see, GPT-4 and GPT-4o, they still try to extract something, but it doesn't make any sense because they are not databases, right? They are not, but as long as you have some Ariston ground truth table, you can do it much better without using any LLM. That's why when we compare AWS and GPT-4o and then our solution, you see that our solution is around 85%, while AWS Comprehend is 56% accurate. And then the cost-wise, it is usually 5 to 10 times cheaper than all these cloud-based solutions, by the way. That's another aspect. If you just hit LLMs or commercial cloud provider endpoints, the cost is piling up again and again, because on the library, if you are using on your local, you have the whole control. You only pay once as a license fee, and then you can parse as many documents as you want. And then just with 1,000 documents, this is what we get. 1 million documents, sorry. This is the cost that you would get at the end of the day. Another task is clinical text identification, because this is the most popular and then clear to explain task of NLP, because due to HIPAA or GDPR regulation, you need to detect all this protected health information, sensitive health information, and then mask them or replace them with the fake entities. Why do you need to replace? Because you need to keep the integrity of the document, right? Most of the time. As you see on this slide, on this page, there is an original task, and then we detect all the sensitive information at first, and then we replace them with the fake ones. And then while replacing it, you also need to keep the consistency as well, right? Like the female names, it needs to be replaced by female names. The countries shouldn't jump from one country to another across the same document, etc. That's why this looks an easy problem, but it's a software solution, not just the NLP solution. And then because you need to because to build such a system, there are different stages that human and software needs to be in the loop. And then most of the time to delivering to the identified data at the last stage requires multiple iteration and then building a complex pipeline. And then it needs to be modifiable by the user according to your own use case because of the data distribution. So there are solutions, of course. We have our own identification solution, and AWS have their own, Microsoft has their own, and Google has their own. And then given the capability metrics, as you see, the Johnson Wallace, the identification solutions cover almost anything, like even the DICOM and pathology and radiology images as well. And then given the text, we already published maybe more than 3 papers so far that can extract more than 15 different sensitive information, because the identification, we believe, is not just a machine learning problem. At first, it's an architecture, it's a software. And then the second, it needs to be modifiable. It needs to be an open box. It shouldn't be a black box. If you are not happy with the name extraction or age extraction, or maybe you are using different patient ID format in your node, and if you just hit any black box endpoint, you will not be able to modify this further. That's why you need to, and then as the name suggests, this needs to be preferably run locally, right? If you want to share your document with the other parties, you would prefer a local identification solution that would work seamlessly without sharing your data with other parties. So we have an online app that you can go ahead and then test right now. It is the id.johnsonwallace.com. Please go ahead and then test it. It can even detect the language at first, across 8 languages. And then it can run the corresponding identification pipeline, because this is end-to-end pipeline that we shipped behind this solution. You can pick the language and test, or you can just make it auto, and then it's going to detect the language as well, and then mask and obfuscate the test that you have. We compared this solution against popular LLMs, GPT-4 and then Claude 3.7, as well as Azure and AWS. As you see, again, like across 6 entities, age, contact date, ID, location, and name, almost all of them, actually all of them, we are about 93 to 98% accurate when it comes to F1 scores, of course. And then the closest one is usually Azure, which is around 85 to 87% accurate when it comes to detecting sensitive information. Then we wrote a paper about this. So we called it Can Zero-Shot Commercial APIs Deliver Regulatory-Grade Clinical Text Identification? Because we already have many customers who are using this in their daily life and then for their production, and then processing millions of records over there. And then we have some lessons learned, and then we wanted to share all these benchmarks and how we built such a pipeline. This is maybe our 3rd or 4th identification paper, which are peer-reviewed, that we published for the last few years. And as you see, it is not only more accurate, it's also much less expensive, right? So the closest one is like 13K Azure. So processing 1 million records for the identification purposes, we are 10 times less expensive compared to other solutions. And then the accuracy-wise, it is better than, like, Azure, as I said, is doing well as well, but it is a bit more expensive compared to our solution. But when it comes to customization, there is no other option than healthcare NLP, which is provided by Johnson Labs. The last one is the DICOM identification. DICOM identification is you have a DICOM images, and then each DICOM images may come with some sensitive data burnt onto the images as well. Or there are some PDF or test reports also written as DICOM file that you cannot process as if it's a free text. And DICOM also has some metadata, header information that needs to be identified or obfuscated as well, because if the patient ID or name, this is already burned inside the metadata that you need to, and it's an easy test when it comes to metadata because it's already a structured information, as you see. But when it comes to image itself, you need to check if the image has a text overlaid or written or burnt, and then you need to mask them. This is what we do as well. So, like, for example, on the left-hand side, you see the original X-ray. On the right-hand side, all the sensitive information is already black boxed mask, right? This is another example, because if you want to share this images with some model vendor to train their own foundational model, let's say, this data should be masked at first, right, to be able to safely share this data with other parties. And then doing this in a DICOM images, like a pathology images, or or radiology images is way harder than doing this on a single written PDF or some free text, right? That's why it's an image understanding and then text detection and then finding the coordinate of the sensitive information and then putting a black box over there. That's why it's a bit tricky, and it's an end-to-end software again, by the way, using visual NLP, healthcare NLP together, and the identification solution, all bunch of solution bundled together, and then we have one image DICOM image identification solution that could work on radiology and pathology images as well. This is another example. And then we compared this to another open source solution provided by Microsoft, Presidio. And then as you see, we created some data again. And then with our largest model, it's around 90%. F1 is 80%, but the precision is 90% compared to 10% Presidio, because Presidio is doing well when it comes to free text. It's for a POC purposes, it's fine. But when it comes to like production grade identification solution, especially for the DICOM identification, which sometimes DICOM images may even come with 20,000 slices inside, which means that you need to find which slices has the text and then also apply the identification on top of this. Our end-to-end DICOM identification solution already does this out of the box, which you can also modify further, as I explained before. So the last topic is clinical note summarization. Over there, the idea is that, with the advent of LLM, right now, all the most popular use case of LLMs are note summarization, because they are doing well when it comes to summarization, but there's a hidden depth over there, which means that hallucination again. By the way, Johnson Wallace already offers hallucination detection tool for LLM-generated medical context. So there is a burden while reviewing all these LLM-generated summaries. That's why we want to evaluate our solutions against LLM. Again, this is an LLM-based summarization. We have MED-S and MED-M, like small and medium-sized LLMs that you can generate summarization. We fine-tuned for this task. We want to evaluate this against ChatGPT itself. Right, and then we ask our physician annotator. We wrote a paper about this as well. Physician annotator to evaluate summaries generated from our models versus ChatGPT in a randomized blind trial setup. And then it's great to see that even a small size 8B size of fine-tuned model is preferred 2 times more than GPT-4o itself. So which means that you may not need a giant LLMs or third-party LLMs when it comes to work on some small task like summarization. It's an important one, but as long as you apply some detection tools, some guardrails against it, you may not need a large LLM to do this. Okay. Thanks for listening to this session. I hope you enjoyed. I hope you enjoy the rest of the sessions as well. Thank you.